Okay, so I'm going to get started and just sort of set the problem up to make sure everyone's on the same page. Everyone's had a chance to get the reaction going. For the video people, we're working on some example problems. So what we're talking about is the Deacon process, where we have hydrochloric acid plus oxygen reacting to form chlorine gas and water. First step is to balance this chemical reaction out. Now, it's totally okay when you balance a reaction if you have fractional amounts of moles. Sometimes it's convenient not to deal with it, sometimes it's convenient to deal with it. Let's say we're dealing with a really big hydrocarbon that we're burning, right? Maybe we care about how much oxygen it takes to burn one butane, but that might involve, 9 halves or something like that. Typically, that's something I'll deal with. But for a reaction like this, I try not to have any fractionals just because I think maybe it'll make it a bit more confusing. So looking at it here, if we've got 2 oxygens coming in, we're going to need at least 2 waters coming out to balance the oxygens, 4 chlorines, 4 of these here, and then 4 hydrogens to get us to here, and then 4 chlorines to get us to there. That is our balanced process. Now, in the problem statement, it doesn't tell us how much chlorine or oxygen is coming into the system. So what do? So we have to assume a what? A basis. So we have tons of control. We could do a basis for water produced, chlorine produced, oxygen in, hydrochloric acid in. So what's a good basis? What do we think? We have 1 vote for oxygen. Any other bases? HCl. Does it matter? No, it doesn't matter mathematically. Practically, though, I would say it is a little bit more convenient to choose one or the other of the hydrochloric acid or the oxygen. What might be more convenient?
The oxygen, maybe just.
So why is the oxygen more convenient?
You don't have to calculate an air ratio.
So we have to still calculate excess, right? No matter what happens, we're feeding in 35. Let's go and read through the problem statement one more time. In the Deacon process for the manufacture of chlorine, we add 35% excess oxygen from air, right? So we have to add nitrogen in here as well. And the fractional conversion of hydrochloric acid is 85%. And we're asked to balance the process using either an atom balance or extensive reaction. Yeah.
Actually, so you can just do the oxygen and then have it be like 100 moles, and then.
So if we had the oxygen as 100 moles, we'd have to back calculate how many moles of hydrochloric acid results in 100 being 35% excess. I personally think that's a little bit working backwards a bit, maybe a bit more confusing. The other piece of information I think why it's better to assume a basis for the hydrochloric acid is because of the conversion. Right? We have a piece of information that says the fractional conversion of HCl is 85%, which means if we choose a nice round number for the feed of hydrochloric acid, that'll mean that we can have a nice round number for the outlet of hydrochloric acid. Yeah.
And you just base that just because it tells you the conversion for.
Yeah, because there's more information I feel like provided about the acid that's important than it is about the oxygen. So ultimately, it doesn't matter, right? So if you were to think about this working on it as a computer doesn't know the difference between 100.0 versus 199.9, for example, right? To them, it's just a computer with 4 digits of precision. But for me, I'd much rather see 100 than 99.9 or some other weird number like that. Same reason why we start meetings at like the 0 and the 15. So I'm going to assume a basis of 100 moles of HCl as my basis. So if I draw out my process flow chart here, I'm going to have 100 HCl entering the system. And how much oxygen do we have coming in?
25 times.
So the theoretical oxygen is 25 then, right? For every 1 OH, you need 4 HCl. Yes? Yes. So the NO2 coming in would be 1.35, 35. So the 1 is the theoretical amount. The 0.35 is the 35% excess. So that'll give us, and I've worked it out already here, 33.7502 entering the system.
And you just did.
So this right here is NO2 theoretical is equal to 25. That's just the stoichiometric amount. For every 4 HCl, we need 1 O2, so this is 100 divided by 4. Then, if we times this by 1.35, that is equal to the NO2 being fed into the system. This is the 35% excess. So we're doing a little bit of quick shorthand, but this is something we're going to have to be familiar with in order to do these more complex problems a bit more rapidly, right? Okay, now, this is the oxygen is being fed from air, so we also need to add in nitrogen. How much nitrogen should we be having here? Let's try and do this. Let's try and do this. Think of the formula in our heads. How do we do this? For every 1 oxygen, or for let's say, if you have 100 moles of air, what's its composition? So it's 21 nitrogen and 79. Sorry, 21 oxygen and 79 nitrogen.
So if you do that,
So what should I times this number by to get to my nitrogen flow rate? 79 over 21, right? 21 O2, 79 N2. So then if I take N2 in is equal to NO2 in times by 79 N2 for every 21 O2. Yeah.
So doesn't that nitrogen only make up the excess oxygen that we have just because?
So in order to get 35% excess based on a basis of 100 moles of hydrochloric acid, this is how much oxygen we need. And then we don't have any control over the composition of air. So if we know that we need 33.75 O2, we have to have, it turns out to be 127 N2. 127.0 N2. Now that's just along for the ride. Right now, as a chemical engineer, you can make the decision, is it worth it to use the free air because you have all this extra nitrogen? Or would it be better to have a purification step where you purify the oxygen and then send only pure oxygen into the process? Right? That's a design decision that you'll be tackling and comparing different options, something you would maybe do in a senior year class. For this one here, we're saying someone else who's a more senior engineer at your firm decided this is the better way to do it, balance the process, right? But in the future, that will be your decision to make. What's the best way to actually run this out? All right, coming out of the system, we have unknown HCl flow rate, unknown O2 flow rate, unknown chlorine gas flow rate, unknown water flow rate, and what else is a species in the system that I haven't written down? Nitrogen. Do we really want to put as an unknown?
No.
So what can we do in our heads? Right, but what is that called? We are doing a what balance? A nitrogen molecular balance. Nitrogen in is nitrogen out. It's not reacting, so we can just write this down. 127.0 N2. Now there's one more piece of information that lets this problem be solved using our approaches. The conversion. Right, so the conversion, so the fractional conversion of hydrochloric acid is 0.85. Now this is in minus out over in. And you know what? I always forget this equation, so let's double check that we got this right. Let's say no hydrochloric acid reacts, okay? That means the in is equal to the out, right? Because nothing's reacting, just like the nitrogen balance. In equals out is 0, doesn't matter what you're dividing by. That would be a 0% conversion. Well, that makes sense, right? Now let's say 100% of the hydrochloric acid reacts. In is 100, out is 0, divided by 100. That gives us 1 as our fractional conversion. So I think this is the right formula. So coming into the system, we know we have 100. We don't know what our hydrochloric acid coming out is, and divided by our 100, and what gives us 0.85 for this number here? How much, what's the HCl outlet flow rate? 15. So NHCl is equal to 15 moles. All right, so let's check that one off. We have 3 unknowns left. So at this point, we could decide to do either the atom balance, or we could do the extent of reaction. So we've done a lot of atom balance examples, so let's actually do the extent of reaction, okay? So, in the extent of reaction approach, let's just run through our heads the atom balance. What different atom balances can we do in this system here? So we have a hydrogen balance, oxygen, and chlorine. Now, which ones do we think is going to be the best to do first? Chlorine looks like a pretty good one, right? Because we know the inlet and outlet here, and we don't know the outlet there, right? So that'll figure this one out here. Okay, what's the next one we could do maybe?
Oxygen.
Oxygen, right, because we know the flow rate here, we don't know the flow rate here, and we don't know the flow rate there. Uh-oh, we run into a problem. We have two unknowns. Right? So the chlorine's pretty straightforward, right? Chlorine in, we know the chlorine out. The only chlorine out we don't know is the flow rate of the chlorine gas, right? Cl2. Oxygen, we run into a problem because we don't know how much unreacted oxygen we have, and we don't know how much water we formed. So if we did hydrogen, okay, let's do hydrogen quick. We have hydrogen coming in, we know this one. We have hydrogen coming out, we know this one here, like the unreacted HCl. The only other thing with hydrogen in it, is the water. Then we can lock in the water, and then the last one we would do is the oxygen. And then from there we would solve for the outlet flow rate of the oxygen. Yeah, question?
Can you just write down one of the equations, just set up
Yeah.
the equations to...
Let's do the hard one. Let's write down the oxygen one, okay? So if we did an oxygen balance, and we can't solve this one, right away, we'd have to do a little bit more work. We have O is in equals out. Now the key thing to remember here, this is an O balance, not an O2 balance. So coming into the system, we have 33.7502, 33.7502 for every one O2 molecule, right? This is molecular oxygen. You have 2 atomic oxygens. Leaving the system, we have to think of all the different ways that we have oxygen. So we can't just look at this right here. We have to look at our process flow chart, right? Because we're not reacting 100% to completion, and we have excess oxygen. So this is not the full picture of what's going on. This is the full picture. We have oxygen coming out in the form of unreacted molecular oxygen, and we have oxygen coming out in the water that is formed when we make the chlorine gas. So we can write out our unknown NO2, and we could write this N dot, right? It's just a nomenclature difference, but in general, we could solve this as a unit of time for minutes, second, hours, right? We've chosen our own basis, right? We can choose whatever basis we want. And if you look at the problem statement, I'm asking for the mole fractions of the product stream. So it actually doesn't matter how much we have. So we have an unknown O2 coming out. Same thing here. For every one O2 molecule, we have 2 oxygen atoms. And we have our unknown water flow rate out. For every one water, we have 1 oxygen. Right, so we've done oxygen balance lots of times. Let's just write Cl balance just for the sake of it. Cl balance. Again, this is atomic Cl, not molecular Cl, which would be the chlorine gas. Coming in, we have 100 HCl. For every 1 HCl, we have 1 Cl. Leaving the system, we know that we have 15 HCl. For every 1 HCl, we have 1 Cl. Plus, we have an unknown amount of chlorine gas being formed. For every 1 chlorine gas atomic, we have 2 chlorine atoms. In this case here, right, obviously we could solve for this one here. Yes?
Why would you multiply that by 4? Because you have 4 moles of base.
The reaction doesn't matter anymore.
That doesn't matter.
Yeah, in an atom balance, we don't care.
Okay.
Right, the atom balance, we don't actually need a reaction to do an atom balance. Right, if we know what compounds are flowing in and what compounds are flowing out, that's totally fine. We actually only needed the balance here to figure out the excess oxygen. Now in the extent of reaction approach, we will need the chemical reaction because we need to know how the different rates of formation and consumption are related.
Thank you.
Yep. Okay, so just for completion's sake, I'm not going to solve it. we'll just write out the H bounds so that everyone has it in their notes and on the video. H bounds coming into the system, how many species have hydrogen? Just one. So we have 100 HCl being fed. 1 HCl gives us 1 H. Leaving the system, how many things have hydrogen in it?
It'd be 2 things, wouldn't it?
2 things, unreacted HCl and water that is formed. 15 HCl is unreacted. So for every 1 HCl, we get 1 H. Plus our unknown water. And for every 1 water, we get 2 hydrogens. Let's look at this. We have 1 equation, 2 equations, 3 equations. How many unknowns do we have? 0 degrees of freedom. So you can solve this as a big matrix. You can solve this by substitution. You can just solve one, then the other, solve it sequentially. But basically, this is a fully defined system, and I don't care how you solve it. This is what I care about. So on an exam, if you give me this with this much detail, I don't care if you don't even put down the right answer, right? I know that you set up your equations correctly. You're going to get everything minus 2 points, for example. Right? The actual number itself is not worth nearly as much as this right here. But the thing is, on an exam, this is pretty detailed, right? I probably get maybe 10%, 20% of the class giving me this detailed of a equation on an exam. Usually I'll get 100, 15, x times 2, right? Which is a lot harder to follow than something like this, right? So if I saw this on an exam and you had all your equations correct, that's most all the points, right? It doesn't matter the actual number that you get. I mean, of course, the last 2 points or so are going to be related to the final number, but setting up the problems like this is the most valuable part, right? And this is the hardest part. But the math itself is whichever you guys feel comfortable solving with. Any questions on atom balance for solving this problem? You've done quite a few of these ones. Let's go to extent of reaction then. So I'm going to write out the general extent of reaction equation and give everyone a few minutes to write down the balances. Yeah?
Sorry, just going back to the, so this is using the atom balance to solve the problem. A moles, and then the moles of...
Oh, okay, yeah. So this on the homework 3, I pulled this from old homework assignments. So these are the answers to 1 digit of precision, to 1 sig fig. So it sort of is a guide. Was that?
So you kind of just gave us the answer here.
Yes, but I need more decimal places for the let's say, for example, the homework.
Okay.
So 0.5 could be 0.48, could be 0.54, right? So I've rounded it to 1 sig fig. So if you see that on your homework assignments, and I made a note of it at the bottom, if you see the A, that's the answer to 1 sig fig, just as so you don't have to go to these solutions to know what's going on, for example, right? Okay, the extent of reaction equation. The number of moles of species I, now this could be at equilibrium, this could be at some arbitrary time, this could be at the outlet of the process, is going to be equal to the number of moles of I initially in the system, could be fed, could be times 0, depends how you want to think about it, plus the stoichiometric coefficient times by this obnoxious squiggly letter called psi that we use as the extent of reaction. Yes?
Sorry, so it's the initial is equal to...
So Ni is the amount after some period of time that we're solving for. Now that period of time could be equilibrium if it's an equilibrium problem, or it could be the outlet if it's, for example, a flow rate problem. Ni naught is the feed or the initial amount. Nu I is the stoichiometric coefficient, and psi is the extent of reaction. So, without blinking, taking a breath, or lifting your pencil off the paper more or less, you should be comfortable writing out this formula for every product species. Not product, but outlet species, rather. Right? So that means you should have 3 equations, right? We're still going to use the conversion to solve for the outlet flow rate of the HCl, but you have chlorine, water, and oxygen. So, in the blink of an eye, use this equation, and 3 equations for the extent of reaction approach. Actually, you know what? Sorry, my bad. You actually need to write it out for all 4 of them. Because we have to actually use this piece of information to solve for the extent of reaction. Yeah, question?
No, sorry.
Okay, sir. So, apply this general formula for the 4 unknown outlet flow rates. HCl, Cl2, oxygen, and water. Using this general algorithm here.
Oh, and for this one, when you do the plus versus the minus after the feed,
This here you mean?
yeah, so sometimes that answer, like, it's Ni, comma, minus that,
So this, I have written here plus, right?
yeah.
Is that what you're asking? So the the stoichiometric coefficient is positive for products and negative for reactants. So the stoichiometric coefficient for oxygen is -1. And so in this generalized formula here, you would be Ni naught minus 1 times the extent of reaction. So this is basically based on the definition of how we define the stoichiometric coefficient. So these are positive, +2, +2, -1, -4.
Gotcha.
And that allows us to keep it so if we keep that system, I don't care if you flip this reaction. Everything, all the pluses would turn to minuses, and mathematically your equations are 100% the same.
Gotcha.
Just like imagine timesing them all by -1. Okay, let's list them. So HCl, NaHCl is equal to 100 minus 4 times the extent of reaction. NO2 is equal to 33.75 minus the extent of reaction. NCl2 is equal to 0 plus 2 times the extent of reaction. And NH2O is equal to 0 plus 2 times the extent of reaction.
So that was flipping it, right?
One more time, say that.
So that's flipping this, the signs, the minuses and pluses.
So, let's break down this one here for the HCl. So, Ni naught, so number of moles of HCl initially or fed to the system is 100. The stoichiometric coefficient for HCl is -4, and times by our unknown extent of reaction. Everyone good on that one? So let's do this one here. Oxygen, we're feeding 33.75. That is the initial or the feed amount. And for every one extent, right, the extent basically tells us how much of this goes to here. So every time this happens once, it takes up 4 HCl's and 1 O2. Now, I could have redone this whole process and said 2 HCl, 1/2 oxygen gives us 1 Cl2 and 1 O2. And this would be exactly the same, but I would just be dividing everything by a factor of 2. It would all work out perfectly fine. Right? My extent would be different because my reaction would be different. For the chlorine gas, I am not feeding anything in, but every time my stuff goes from the left-hand side to the right-hand side, I make 2 of them, and same thing for the water. So, this one right here has 0 degrees of freedom. We only have one unknown, so we can solve for our extent of reaction. And in this case here, we solve for the extent of reaction, and let me make sure I don't do this all in my head. I have it written down here. We get that the extent of reaction, this is 15, right? We had already solved this from the conversion, would be 21.25 moles. Yes?
Sometimes the extent of reaction is negative, and that just means the equilibrium goes to the left, right?
Yep.
So then when you plug that into your equations, do you use the absolute value?
No, you keep it negative. So if we had written this backwards, let's say, right? if I had written the CLs over Cl2 over here and the HCl over here, what would have happened was this would have been positive, positive, negative, negative. I would have just switched the signs of everything. So when I solved for this, I would have had negative 21. Right, but then this negative would cancel with this negative and everything, right? So everything would work out exactly the same. So this is especially the case when you're working on an equilibrium problem, right? If you have products and reactants fed to a process and you don't know where the equilibrium lies, it could go to the right, it could go to the left, but we don't care. As long as we stick to this convention, however you write your reaction, this is the key thing, you have to be consistent internally. If you write your reaction this way, with HCl on this side and Cl2 on this side, and you keep your convention consistent, where you're minusing your HCl and you're plusing your Cl2, right? Whatever this number is here, just roll with it. You just take this number right here and you directly substitute it back into each of your 3 other equations, and it'll all work out. But if you change right way halfway through, if you change the negative to positive, then it's going to be gobbledygook. Right? So you have to be consistent internally. So if we just substitute this number here, 21.25, into all of these expressions, we can solve for the answers. And these are all one equation, one unknown. So for oxygen, we get 12.5 moles of O2. For chlorine, we get 42.5 moles of Cl2. And for water, we get 42.5 also. Oops, O2. H2. All right. And then the problem statement itself, it says calculate the mole fractions. Basically, you just add them all up. Don't forget about the nitrogen. And then you can calculate those values there. Questions? How does everyone feel about extended reaction approach? Personally, my favorite is the extended reaction, if you know the chemical reaction. If you don't know the chemical reaction, atom balance. If you have multiple reactions, extended reaction still works really well. Atom balances can somewhat get a little bit hairy when you have a big complex system with lots of things going on. Because then every single balance has like 8 terms in it, right? The flow rate, the conversion factor, the flow rate, the conversion factor, the flow rate, the conversion factor, right? So it just takes a lot of space up. So as systems get more complex, that was pretty straightforward. That was not too bad, right? Just a small little space, yeah.
So if you have multiple reactions going on at once, would you have multiple extended reactions?
Bingo. So let's generalize this expression here for multiple reactions. So we'll still have Ni, that's what we care about. I is the chemical species, equals Ni naught, number of moles of species I initially are fed to the system. But in this case, it's going to be a bit more complicated. Summation for J is equal to 1 to the number of chemical reactions, nu I J extent J. This is the generalized form. It looks unpleasant, but it's not too bad. So what we're saying is the number of moles of species I leaving the system is equal to the number that we feed, plus or minus how much is formed or consumed in any given reaction. So some reactions, maybe some product will be consumed in both, in which case you'll do minus extent 1, minus extent 2. Maybe it's consumed in reaction 1 and formed in reaction 2. Minus extent 1 plus extent 2. Right? So you just basically add them all together. So example, yes, let's do a quick example. So let's say we have A plus B goes to C, but C can go to D. And let's say that B can go to E, for example, right? And in real systems, you can have hundreds or thousands of reactions going on simultaneously, right? Especially in petrochemicals. So let's look at B, because B is a bit more of an interesting one. So we have N of B is equal to N of B naught. So what reactions is it participating in? We have extent 1, extent 2, and extent 3. So what reactions are B participating in? 1 and 3, right? So should I add or subtract this one? How much? 1 extent 1. What else?
And then plus,
minus 1 extent 3. So this term right here is nu of B reaction 1, and this is nu of B reaction 3. So in this case, the B is the I, and the 1 is the J, the B is the I, and the 3 is the J. So for every reaction, each species has their own stoichiometric coefficient. Now let's look at C, for example. So we have N of C fed is equal to N of C fed initially plus extent 1 minus extent 2. And then you can repeat the process for A, D, and E, and so on. Yes,
so those
question?
extents are going to be different then, right?
Yes.
Okay.
So extent 1 and extent 2 and extent 3 are independent extents of reactions. So you would have to solve for them individually. So it increases the number of degrees of freedom that we have substantially.
And you did a minus just because it went from C to D? Or,
For this last one here, you mean?
yeah.
So in this one, let's break this one down. So C, the outlet amount, is how much is fed plus how much we're generating in reaction 1, but minus how much we're consuming in reaction 2. And then that's the net amount that is formed or created in the process. And then we could repeat the process. So let's say, for example, let's just do it in our heads really quickly. So A, we have our equation is NA equals to NA naught minus just extent 1, right? NA is equal to NA naught minus extent 1. And let's see, 1, 2, 3. So we're missing D. So ND is equal to ND naught plus extent 2. And the last one is E. NE is equal to NE naught plus extent 3. So we need 3 pieces of information to balance that particular example. Right? So we need conversions or some outlet flow rates or some piece of information to make us through the system. Any questions? All right, now we don't have a ton of time for the next example, so I'm just going to set it up. We're going to read through it because it's similar. It's the ammonia process again. Okay. Ammonia is formed from hydrogen and nitrogen. This is the Haber process. We've already talked about that. The feed rate of hydrogen is 90 moles per second. Okay? Nitrogen is fed at 200% excess. The overall conversion of hydrogen is 90%. The separator removes 100% of the ammonia in the bottoms without any H2 or N2. The top stream from the separator is partially recycled and has a purge stream to prevent the buildup of nitrogen. Purge stream is 10% of the stream entering the splitter. So we're not going to have time to solve it, but we have time to set it up. So there's a lot more stuff going on in this problem than there was in the first example. So this is a reactor separator. So let's first draw out our general reactor separator. Now, you don't have to stick to this convention, but for some reason, this is what I always seem to do. I say 1, 2, 3, 4, 5, 6, 7. This is our feed. This is our mixer, where we mix the recycle stream. This is the recycle. We have our reactor. We have our separator, a bottom stream, and a purge stream. This is a splitter. So let's start filling in the information that we have. So we know that the feed of hydrogen is 90 moles per second. So we'll say 90 H2. Just knowing that when we actually come up with our final answer, we may have to add back our units of moles per second, or maybe it's moles per hour, or whatever the case is. But for shorthand, to keep it simple, I'm just going to write 90 H2. It's fed with 200% excess ammonia. Oh, well, I guess we got to balance our reaction. All right, N2 plus H2 goes to NH3. So let's see, let's do the nitrogens. 2 of these, 3 of these. Right?
Yeah.
So, what is the stoichiometric amount of nitrogen necessary to consume 90 hydrogens?
30.
30. We could say theoretical or stoichiometric. Okay, now what is a 200% excess? Is that times 2? Or is it times by something else? So what's a 50% excess? 1.5, which can put us at 45.
So it's 4.
So what is a 100% excess? That'd be double. So 200% excess is the 100% it takes to normally do it, plus 100% excess, plus another 100% excess. So that puts us at 90. So this would give us 90 N2. It's not 2 times, it's 200% in excess of what we already needed. Okay, so let's keep going down the list now. So we've gotten through the feed, the excess nitrogen. Now the overall conversion of hydrogen is 90%. Well, I think we're a little bit stuck on how... Well, so there's a couple things we have to look at. So we have 2 types of conversion. If you look at your questions here, we have what is the single pass conversion of hydrogen? But you're already given the overall conversion. So overall conversion means I'm going to put a big box around this whole process, and I don't care what happens on the inside. Right? And in fact, some reactors are designed this way, where the separation is actually occurring inside of the reactor. But we can balance the process by thinking of it as separate units inside the same box. So the overall conversion tells us how much hydrogen leaves the overall system in either the bottom stream or the purge stream. But if we read through our problem statement here, it says that 100% of the ammonia is in the bottoms product without any hydrogen or nitrogen, which means that we don't know N ammonia or N stream 7 ammonia, right? Because we know that there's no hydrogen or nitrogen in there.
You mean N4, right?
4, yeah, sorry. So that means we know that all of the hydrogen and nitrogen is coming out of the top here. So N6 nitrogen and N6 hydrogen. Now this splitter here, this is sort of a dumb unit operation, right? It's not doing anything other than just redirecting some flow this way and redirecting some flow that way. So we know there's no reaction going on because it's just a splitter. So then we know that we would have an N5 N2 and an N5 H2. We could also make the same leap of logic from the separator, right? If all of the ammonia goes out the bottom and all of the other gases go out the top, right, then we would work through here and work through there. So if we're feeding only nitrogen and hydrogen to our splitter, the splitter can't change the composition. It only changes how much goes from one direction to the other. In this case here, we would say N7, N2, N7, H2. We come back around here. We're mixing hydrogen and nitrogen with hydrogen and nitrogen. So we have N2, N2, and N2, H2. Now, if we work backwards from the separator is being fed with ammonia, nitrogen, and hydrogen. This separator is not a reactor, right? So I'm just changing the relative compositions of things. So here we have N3 ammonia, N3 N2, N3 H2. Right? We're just setting up our problem so far.
So would a total balance for the N2 and the H2 be the best approach?
That would be a very, very good starting point. So, let's just, for the sake of argument, let's do a a balance in our head on the mixer. Okay? We have 1, 2, 3, 4 unknowns. How many balances do we have for the mixer? 2, right? It's a non-reacting system, so we have 1 balance per species. We can't solve this system, right? We need 2 additional pieces of information. Let's look at the reactor. 1, 2, 3, 4, 5. Of course, we have no idea what's going in, what's coming out. We can't solve that, right? But let's look at the overall process. Coming in, it's fully defined. And we have 1, 2, 3 unknowns for the overall process. Well, we're getting pretty close there, right? But let's use our last piece of information here. Well, we say that the top stream from the separator is partially recycled. Sorry, my bad. Overall conversion of hydrogen is 90%. So hydrogen conversion, so H2 conversion. So 0.9 is equal to in minus out over in which case here we have 90 minus N6H2 divided by 90, which means N6H2 is equal to some number that I have written down here, 9 moles per second. And we're starting to break into the process now. So now we have 2 unknowns, and we can solve it using an atom balance and extensive reaction. So if we do an atom balance, we've got this one done here, right? We can do an overall balance for a reacting system using either an atom balance or an extensive reaction approach, in which case we can get the ammonia and the nitrogen coming out. Right? When we draw an overall balance, what we're doing is we're converting this system to just like this. N2 H2, N2 H2 ammonia, 90% conversion. Right? This is an overall balance. We're just looping the whole thing around. Okay? Now, the one thing that I really want to emphasize before we go, last piece of information talks about our splitter. So the purge stream is 10% of the stream entering the splitter, meaning 90% is recycled. The key thing is translating this to an actual equation, in which case we could say that N6 is equal to 0.1 times N5. Since we know, right, that the splitter's not changing the composition of anything, we could also say that N6 of nitrogen is equal to 0.1 N5 of nitrogen. We could also say that N7 of nitrogen is equal to 0.9 N5 of nitrogen, right? That's our last design specification. So now the key to this reactor separator problem is we got to work our way in from the back. Now, one of the questions on the sheet here says, what is the single pass conversion of hydrogen? That is asking for the conversion here.
Is that just through the reactor?
Yes. So, when these gases go through the reactor one time, that's a single pass. Some of it gets recycled back, has a second pass, third pass, fourth pass, right? So this overall thing is after all the passes go through. Yes?
And that conversion would just be the same thing as, so it'd be the N for the N2.
So we would define this as the single pass conversion. Some unknown number x would be in minus out over in. So for hydrogen, it would be N2H2 minus N3H2 divided by N2H2, right? That would be the single pass conversion. Is it going to be higher or lower than the overall conversion? Lower. If it was higher, it wouldn't make any sense. We wouldn't have to do the reactor separator process. Right? Since it's lower, we're going to recycle the unknown unreacted hydrogen and nitrogen back through the system until we get a higher overall conversion. But from here, it's no different than what you've done already. So the setting up the problem is the difficult part, and then mathematically trying to figure out how you can write your design specs as an equation as a function of your unknowns. Question?
So I just want to make sure I follow what you said. So you use the flow rate after the mixer to Even
Yes.
though what came in from the recycle is technically going through the septic tank.
True, yes. Yeah, but molecules are indistinguishable, so we don't actually know which one's gone through and which one hasn't gone through. But yeah, so the single pass conversion would be the feed to the reactor relative to the outlet of the reactor. Okay, have a good week. So one thing, my office hours on Thursday will be shifted a little earlier because I have a defense to attend, but I'll send out a message. I think it'll be 11 to 1.